Greetings, our project is a PDA-based HTML tag matching validator. In modern web development, HTML defines the structure of website. However, common mistakes like unclosed or misnested tags can cause rendering issues and inconsistent layouts. This motivated us to create a validation system that can automatically check the correctness of tag nesting. We focused on solving this using a push-down automaton, since tag matching follows a last-in, first-out logic, which perfect for a PDA stack. Our model checks whether every opening tag has a matching closing tag, ignoring self-closing tag or attributes, so that we can target the core structure in a more reliable and efficient way.
So why is this the perfect tool for validating HTML? Because HTML structure is inherently nested and follow the exactly same last in first out logic, when our validator sees an opening tag like div, it pushes a symbol for it onto the stack. When it sees a closing tag div, it pops the top system and check if it's matched. If it is, the structure is correct. A simpler machine like a finite automata can't do this because it lacks the memory to know which tags are waiting to be closest.
This is our proposed solutions and HTML text structure validator using push-down automata. We used PDA because its stack is ideal for tracking nested text, something finite state machines cannot handle. When it reads opening text, it will push to the stack. When it reads closing text, it will pop and compare. The text content is ignored. The document is valid if all inputs is read and the stack ends empty or with only the initial symbol Z. Is invalid if tags are mismatched. A closing tag appears with an empty stack. The stack is not empty at the end. This system uses a push-down automata to validate the structure of HTML text through 5 main steps. First, organizations. The HTML is organized. We extract only the text, ignoring self-closing tag and comments. Second, initializations. PDA start with an empty or with start stack variable stack to track open text. Third, tag processing. As we read each token, opening tags are pushed to the stack and closing tags are popped and matched. If a mismatch or extra closing tags occur, it's reject. Fourth, final validations. If the stack is empty at the end or only left the start stack variable, the structure is valid. Otherwise, they are unclosed stack. Finally, output. The result is simple, either valid or invalid, to help detect the structural issue quickly. This is the formal definitions for the PDA design. The schema is a set of input symbols, which are the HTML text that would occur nested tags like div, ul, and li. The gamma is a set of stack symbols where A represents the read for div category, B for ul category, and C for li. This is the valid HTML structure example. On the left-hand side is the original input. It will filter out the irrelevant input, and on the right-hand side will be the input for the HTML structure validator. Initially, the stack only has Z variable, which is the start stack variable. When we read div, which is the opening tag, so we will push A into the stack. When we read again div, so we will push again A into the stack. When we read ul, so we will push a different variable, which is B, into the stack. When we read li opening tag, we will push C into the stack. And when we read the close tag of li, we will pop C. Same with the li, we will push C into the stack and pop again, and also push again C when we read li, and then pop again when we read the close tag of li. So when we read the ul close tag, we will pop B, and for the close tag for div, we will pop A, and lastly we read div close tag, we will pop A again. And now the stack is valid where the Z variable only remains in the stack.
This is the GUI for our HTML tag validator with the simulation of PDA in last-in, first-out manner. So from the front end, you can see that user can input the HTML code over here, and it will display the validation results and also the tag analysis so that the user understands why it is unmatched or matched. Right now, let's have a try with valid code. Paste it and we click validate HTML. From here, we can see that valid HTML structure, it shows that it's valid, and for all the valid tag, it will display in green color. For the tag analysis, it will display each tag name and also the total number of open and closed tag and also the status. From here, we can see that all the status of each tag is matched. So for all match status, we won't display any reason. Let's have a try with invalid. From here, you can see that it is invalid HTML structure. For, for any invalid HTML tag, it will display in red color. From here, you can see that, oh, it is unmatched. So over the table, you can see that division. For division, it shows that the tag mismatched because from here you can see unordered list. So in here, it should be unordered list first. So the reason is shown over here, tag is mismatched, expected unordered list, but found division. Then for the unordered list, it will show that it is also unmatched because you close division too early. You should close the division over here. So it will show that out. Please close unordered list first. So from here, the developer can identify whether their HTML code is valid or invalid or not by using our HTML tag validator. This function simulate PDA is the brain of our validator. It simulates a pushdown automaton using a stack. Opening tags are pushed onto a stack and counted. When a closing tag appears, we check top of the stack. If it is matched, we will mark it as valid, and if it's not matched, we will mark it as invalid and log the reason. We also detect the missing closing tags after passing. And finally, we return whether it's valid, all token status, tag counts, and detailed mismatch reasons. We implemented a pushdown automaton for HTML tag validation to ensure structural integrity and accuracy. The PDA used a stack to track opening and closing tags, especially in nested structures, which finite automaton cannot handle due to limited memory. Since HTML is a context-free language, PDA is the most suitable model to recognize it. It detects the tag mismatch or unclosed tags and help developers to identify this error quickly. Our system follows a modular design with four-phase tokenization, initialization, tag processing, and final validation, making it easy to maintain and extend. This shows both strong software engineering practices and a practical application of automata theory.
While our current model is effective, there are several ways we can enhance its power. First, we can expand it to support the full HTML specification by correctly handling self-closing tags like image and ignoring comments. Next, we can add another layer of validation to check the attribute within the text, ensuring they are formatted correctly. Finally, for more advanced analysis, we could translate our PDA model into a context-free grammar to compare its performance against other formal parsing techniques.
In conclusion, our project successfully solved the challenge of validating HTML tag nesting and closure using PDA logic. The stack-based design handles unbounded memory, making it ideal for tracking tag structure in a last-in, first-out manner. Our PDA validator ensures that the tags open and close, which is crucial for consistent web page rendering. It also detects and localizes structural errors, helping developers to identify mismatch or unclosed tag quickly. By automating the validation process, we reduce manual effort and human error. This project demonstrates how automata theory can effectively solve real-world problems, especially in document and language processing. That's all for our group presentation. Thank you.